So last but not least, next speaker is Professor Vassilis Kostopoulos. He is a director of Applied Mechanics and the Vibration Lab in University of Patras, Greece. He has 30 years of experience in the field of composite and aerospace structures. He has a wide research interest, including the fracture and the fatigue of composite materials and structures. Today, he will give a talk about an innovative material model calibration procedure for enhancing the fidelity of numerical solution in the case of impact loading of composites.
Good afternoon. First of all, I would like to thank Professor Zelubino and the KAUST team for the invitation to participate in this workshop and the opportunity they gave me to present you some of our recent results in the field of impact loading of composite structures. The topic of my today's presentation is about the development of an innovative material model calibration procedure for enhancing the fidelity of numerical solution in the case of impact loading of composites. As we all know, impact loading of composites is among the most critical loading cases, and this is because of the development of multiple delaminations within the composite structure. And we know also that these delaminations deteriorate the integrity of the structure, of course, decrease their structural performance. What I will try to do is to show you a way for the calibration of material model that we use in the case of an impact loading of composites in order to converge the numerical findings with the experimental results. This is not an easy task, and this is what is required in the majority of the cases. The outline of my presentation includes some introductory information, the objectives of the present work, the analytical description of the calibration of the algorithm of the material model, and some conclusions and some proposals for future work. There is an escalating use of high-performance composite materials recently due to their high specific properties, high specific modules, and high specific strength. This is what this ASPI diagram shows. Composite materials is around here. You may find composite materials everywhere in applications in defense, aerospace, space. You can also find them in everyday structures, you can find them in automotive industry. Composite materials, due to their lightweight, can be identified everywhere. As extensive is the use of composite materials, is also very often the effect of impact on the composite materials. So in this picture, you may see some examples coming from the field of aerospace, where tool drop, runway debris, bird strike, or hail impact may happen. Also, in each accident, there are many cases of impacts that take place. And for example, in the case of aero engines, if you have a blade out, then this high velocity impact component must be contained, and the composite material case is the one that contain finally this broken blade. Let's now try to focus on the objectives of our work. The objectives of the present work is the development of a material calibration procedure that will be based on a series of quasi-static mechanical and interlaminar fracture tests. What we propose is to work with the known experimental curves and to try to optimize the set of material data in a way that we can simulate numerically all the experiments in a reliable way. We have proven that using the optimized set of data coming from this process, we may simulate the impact tests, either of a low or high velocity impact, and of a moderate energy level, very precisely. How we demonstrate the validity of our proposal? Well, the material that we use for demonstrate the validity of our proposal was a Cytec SciComm 977 UD prepreg. All the coupons used was manufactured using autoclave, and we conclude to a volume fraction, fiber volume fraction close to 62.5%. We perform all the necessary quasi-static tests for characterizing the material, both nominal properties plus the interlaminar fracture properties. And in all the cases, we monitor the force displacement diagrams that we use for the optimization process. As you may see, we perform tensile test in 0 and 90 direction, compression test in 0 and 90 direction, in-plane shear test, and then interlaminar fracture toughness for mode 1 and mode 2, open hole tensile test, and the ILSS test. The mechanical characterization test was made according to the ASTM standards. The interlaminar fracture toughness test was made, and the open hole test was made using the Airbus standard, and the ILSS was made using the EN standard. As I told you earlier, the core idea of the present work is to determine a set of optimal material properties, both mechanical and interlaminar fracture ones, that will model the experimental tests performed as they showed you earlier. Then, in this slide, I'm going to show you the numerical tools used and the assumptions made for the implementation of the idea. The FEM code that we use in this work is LSDyna software, and in the majority of the tests we used LSDyna implicit. Only in the case of ILSS simulation tests we used LSDyna explicit, due to the fact that it is capable of handling contact nonlinearities without convergence difficulties. The model used 3D elements, the stack solid method, and using solid element instead of thin or thick shells, no geometric or loading assumptions are required, as well as the boundary conditions are treated more realistically. The solid elements allow the 3D behavior of simulated components to be fully captured. The material model considered is an elastic orthotropic material model with 4 failure criteria, and the failure criteria considered is the Chang-Chang failure criteria for tensile and compression failure of both fiber and matrix material. For the interlaminar fracture properties, cohesive zone methodology was used. The basic advantage of a cohesive zone model method is that the locus and direction of a crack initiation is not needed to be predefined. Then, in the case of impact, which is the final application of the current work, the locus of damage initiation is not obvious. During this work, the convergence test was very precisely checked, and the mesh influence analysis was carried out in that way that time-efficient FEM models were developed. In this diagram, the application of the proposed methodology is shown schematically. The data that we have available are the load displacement curves, stress-strain diagrams, coming from the experimental tests. Mod Frontier software combined with the MATLAB was used for the formulation of the calibration algorithm. The calibration algorithm is based on the comparison of the numerical force strain or force displacement curves with the corresponding experimental ones that are available. The finite element models, which are mentioned in the previous section, constitute the numerical part of the current algorithm, whereas the experimental testing results were defined as the target of the optimization routine. For minimizing the parameters combination, the calibration process was divided in 2 stages. The first stage includes the in-plane loading tests, tension in 0 and 90 direction, compression in 0 and 90 direction, shear test and open hole tests for the calibration of the orthotropic material law. Whereas in the second stage, which consists of the fracture tests and the ILSS one, we try to calibrate the cohesive zone model. This is clearly indicated in this diagram, where in the left you may see the calibration of the orthotropic material properties, and in the right you may see that how the process of the calibration of the fracture in the laminar fracture test and the ILSS test is taking place. The first stage of the work uses the calibration of material states. The optimization target is to minimize the root mean square error between the curves and the numerical results, and also a very critical target is the minimization error between the numerical and the experimental maximum load that are given by the curves. In this figure, the optimization algorithm is shown in more details. As we stated earlier, we follow two-step optimization. The first step deals with the optimization of the orthotropic material model, and the second step deals with the calibration of the cohesive zone model. As you may see, in the first step that deals with the optimization of the orthotropic material model, we compare numerical results against the experimental ones. MOGA2 algorithm was used for the optimization. MOGA2 is an improved multi-objective generic algorithm, and MOGA2 is an efficient optimizer that uses smart multi-search elicit method, preserving excellent solution without bringing premature, non-feasible convergence. MOGA2 optimizer can use two methods of generating a new population of data, the crossover technique and the mutation technique. In this work, we used the mutation technique for the generation of the new population of data. After the convergence to the optimal material properties, the algorithm stops, locks these values, and start the second step of the algorithm that deals with the calibration of the cohesive zone model. Some additional characteristics are shown in this figure for the optimization algorithm. What I would like to stress is that in the current study, for the reduction of the computational time, but for keeping the spread of the initial values to the design space, the Latin hypercube scheme was adopted. The Latin hypercube scheme is a constrained Monte Carlo sampling scheme where the constraint refers to the way each variable is sampled. The cumulative distribution function is split in n intervals with the same probability, and then a random value is selected within each interval according to the density function. Thus, the points are relatively uniformly distributed over the density function range, whereas the Monte Carlo scheme, the values are chosen independently according to the global density function without considering the previously generated scheme points. In that sense, Monte Carlo is a memoryless algorithm. In the right part of this figure, you may see what are the parameters that has been calibrated for the orthotropic material model. And as you may see further to the typical material properties, we have also calibrated the alpha parameter for the shear nonlinearity. And for the cohesive zone model, the second stage of the optimization scheme, further to the typical values of G1C, G2C, peak traction and peak shear, we also conclude to the normalized separation peak traction, L naught, and the exponent of the power law for the mode mixity criterion. Normalized separation peak traction, L naught, deals with the actual scheme of the traction separation load, and the exponent deals with the mixed mode criterion. In both cases, the objectives for the optimization were the RMS values for the curves and the RMS for the maximum force error in plane shear, while in the second stage of optimization scheme, the five objective functions were the curves in mode 1, mode 2, the RMS for the maximum load and the RMS for the ILSS test. After the application of the two-stage optimization scheme, we conclude to these material parameters. These are the optimal set of material parameters that has been calibrated, and in this figure has been framed with this red line. Among the things that I would like to stress is that the elastic moduli that has been used is the tangential elastic modulus, and you see that there is a significant correction from the nominal value to the calibrated one, and also through this optimization scheme has been calculated values that was not available in the first approach of the available data. So out of plane CR modulus has been calculated. The Poisson ratio in plane and out of plane has been also calculated, and the nonlinear shear stress parameter has been also calculated. So having these values in place, now we will try to see what are the corrections that we have made based on the nominal values and the optimized values that has been calculated. Now let's see how to use the optimized calibrated material model parameters, both orthotropic material behavior and the cohesive zone model that we have allocated to this material. And let's try to see the numerical simulation of the mode 1 experiment shows what shows the mode 2 simulation experiments and what shows the interlaminar shear strength experiments. Let's go in the top left diagram over here. The solid black line is the experimental results. The red line is the simulation of the experiment, mode 1 experiment, in case we have used the optimized material parameters. Finally, the dot line curve is the simulated mode 1 experiment in case that the reference material parameters has been used, not the optimized one. As you may see, the optimized material parameters are extremely close to the experimental data, while there is a significant difference between the experimental data and the simulated experiment in case that we have used the reference material properties. It is important to notice that the difference in the top load is close to 106%. If we go in the top right diagram, here you may see the simulation of the mode 2 experiment. The results of mode 2 experiments are shown with the solid black line. The red line represents the simulation of the mode 2 experiment in case that we have used the optimized material parameters. And the dot line over here is the numerical representation, the numerical simulation of the mode 2 experiment in case that we have used the reference material parameters. As you may see, there is also a significant difference of close to 20% between the higher the top load in the case of mode 2 experiments. The same situation can be identified also in the case of interlaminar shear strength experiment. The solid line again is the experimental data, the red line is the simulated data using the optimized material parameters, and the dot line over here is the simulated experiment in case that the reference properties has been used. Again, you may see that there is a significant difference both in the maximum load, but also in slope of the response of the material. So it is clear that using the calibrated data, at least in these representative experiments, the simulation of the experiments are very close to the real experimental data. Now, let's try to recall why we have made all this calibration of the material model. The idea behind is that we are trying to use this calibrated data in order to simulate the impact test, and we believe that using this kind of calibrated data, simulation will be very close to the reality. So what first we have done? We have done low velocity impact test on CFRP laminates made by the same material as the one that we have already calibrated. And the idea is that we have this impact tower. We use this quasi-isotropic layup plus 45.0 minus 45.93 symmetric. The dimension of the impact sample is given here. And of course, the volume fraction is the typical volume fraction that we have already used. We use an impact velocity close to 4.3 meters per second, and an impact energy close to 30 joule. In this case, we have simulated this experiment, and of course, we have used here the optimized material parameters. We have used the LSDN explicit for the simulation. Again, as in the former work, we have used fully integrated first order 3D solid elements, elastic orthotropic material with the failure modes that we have already described. Of course, fracture based on the interlaminar failure. And of course, the material model parameters delivered by the calibrated algorithm. Among the things that I would like to stress here is that in the case of energy, of the absorbed energy, there is a deviation from experimental data to the calibrated simulation material model close to 13%. This is not something that we can ignore. However, we are very convinced that this is due to the material model that we decided to use and the failure criteria, because we use the Chang and Chang failure criteria, which does not consider the out-of-plane comprehensive matrix failure. So, to our opinion, if we use a different material model, this deviation will not be there. What we saw earlier referred to low velocity impact. Here we try to simulate experiments of high velocity impact. Let's see the experimental data for the high velocity impact. We use an impact velocity of 85 meters per second. We have used a mass of 8.4 grams for the impactor, and this is a stainless steel impactor of having a diameter of 12.7 millimeters. This experiment has been made by using an air gun, and of course we have tried to simulate this experiment based on the same methodology that we earlier described, meaning that we use LSDN explicit, we use 3D elements, we use the same optimized calibrated material parameters, and of course the only changes is the projectile and the clamping devices. Unfortunately, here we had the possibility of capture the contact force versus time plot. However, we can simulate the kinetic energy of the projectile, and we can see that the kinetic energy of the projectile is much closer to the results that are gained by the calibrated material properties. The most important result following an impact event is the developed damage. In our case, due to the level of the impact energy chosen, the damage is only delamination. In these figures, in the left, you are going to see the delamination in the case of low velocity impact. In the right figure, you are seeing the delamination in the case of a high velocity impact. The white area is the result of C-scan in the case of experimental tests. The red area is the result, the delamination result concluded after the simulation of the test, the impact test, using the reference properties of the material, while the black line area is the simulation result of the delamination using the calibrated material properties. It is clear that the calibrated material properties is much closer to the experimental results, although there is still a deviation which is in the case of low velocity impact is at the level of 10%, while in the case of high velocity impact is at the level of 25%. This deviation is related to some of the assumptions made. The most important assumption made is the results that we have used in the case of Mode 2 experiments, where based on the experimental setup, we consider the pre-cracked specimen and not the non-pre-cracked specimen, because in our case we used the AIM, the Airbus experimental setup, and this is based on pre-cracked Mode 2 specimens. In case that you are not using pre-cracked specimens, and the Mode 2 fracture toughness is much higher. Another parameter that we haven't taken into consideration is the mode mixity, and in a future calibration scheme, I think that the mode mixity must be taken into consideration seriously. Following the identification of delamination area and the comparison between the experimental and the numerical results of the delaminated area, now we consider the compression after impact test, and in the top you may see the results in the case of low velocity impact, while in the bottom you may see the results of compression after impact in the case of samples that has been exposed to high velocity impact. You may see in both cases, low and high velocity impact, there is a very good capture of the maximum force that the impacted component, the impacted plate fails. There is a difference in maximum force at the level of 1%. And also it is very well captures the behavior of the material. If you see in the pictures, you see also that the way samples fail is also captured very well in both cases, in the case of low and high velocity impact. So this simulation is also very successful using this calibrated material data. As concluding remarks, we may say that in this work we propose a multi-stage material calibration model that can be used for the simulation of impact tests. It is at the level of the energies that we try in this work. The results was very promising. Not only the delamination area, not only the peak load, but also the behavior of compression after impact was captured very precisely. The developed methodology comprises an effective and time-efficient method for the definition of material model parameters, minimizing the effort needed for raw data processing and the complexity of the problem in case that you would like to have a reliable material model for simulate some experiments. And some numerical parameters which cannot be calculated directly from the experiments. Using this calibration procedure, you can have also these results in order to use this in the analysis. It is clear that the proposed work, the proposed approach has many ways of improvement. First of all, someone has to try to see up to which level of energy this is valid. We have to check also the case of mixed mode and how we can consider this mode mixity in the results. And of course, we have to take into consideration whether it is necessary to use pre-cracked or not pre-cracked samples in the case of Mode 2 experiments. But the most important point is that we have to very carefully see which is the level of use of this kind of approach. Thank you very much for your attention. And in this publication, you can find more details about this kind of work. And I would like to thank my colleagues in the University of Patras, Vassilis Kostopoulos, George Sotiriadis, and Thimis Giannaros for their contribution to this work. Thank you very much.
Thank you, Professor, for the nice work. So now it's open for the question. So do you consider all the experimental results such as tensile, compressive, shear in the calibration or only few of them? If only few, then which one?
We have considered in this calibration process all the quasi-static tests that we had available. So this means that we have considered all the set of characterization. This means 0-90 tension compression plus CR tests, and also for the calibration of the orthotropic material properties, we have taken into consideration the open hole behavior. And then, in the case of in the second stage, we calibrated the cohesive zone model, and then we use as the experimental test that we check all this, the ILSS test. So we use all these parameters. So we have in each experiment, we have these 7 coupons that we have tested. We have taken the mean value of these 7 coupons, and we try to through the simulation and the optimization to reproduce these values.